Good morning, everybody. It's Martin Fair here on behalf of SLCan. I'm very pleased to welcome you again to our monthly webinar series. Today, we're very pleased to have Dianthe van Weerden here with us. She is going to do a presentation, as you can see on your screen, talking about CFD and how does she make it cheaper. Just a little bit of a background information on Dianthe. She's a technical coordinator for RWDI, a graduate of the University of Waterloo's Bachelor of Applied Science program with honors in systems design engineering. Dianthe is a versatile member of RWDI's building performance group, delivering analysis on issues ranging from internal ventilation to building aerodynamics and wind-driven rain. She's contributed to the success of demanding engineering projects around the globe, including transit stations, high-rise buildings, hotels, and specialized indoor environments like laboratories. As is always the case, I would ask that if you have any questions, that you please feel free to type them in the dialog box on the GoToWebinar dialog box, and we'll deal with them at the end of the presentation. Without further ado, I will turn it over to you, Dianthe, and it's all yours.
Thanks. Thanks everyone for listening. Today's presentation is what CFD is so expensive and how do I make it cheaper? So to start off with some acknowledgements, this presentation is a group effort between myself and my colleagues. The content is not all mine, so they provided a lot of the cool images as well that you can see. And a big thank you to Eric, Lee, and Vincent Tang, who helped me develop this webinar and gave a lot of feedback when putting it together. So as an outline of what we'll be covering, there'll be 3 points. So the first is the value of CFD. The second will be defining project objectives and constraints. And then the third will be minimizing cost while maximizing value. So, as a start, why do CFD? It should have autoplayed, but of course now it's not working. But it's a pretty cool video just to illustrate some of the things we can do. But unfortunately not playing. So, the value of CFD. So CFD, or computational fluid dynamics, gives you a 3D simulation of air movement within a space. So in contrast with traditional engineering calculations or experimental testing, CFD can be used to get a comprehensive picture of the variations of airspeed, temperature, and the concentration of contaminants within a space. CFD can also be performed pre-construction to assist with design decisions such as mechanical layouts and fan sizes. So to continue on that, if we look at these images, they're plotting temperature in this lab space we saw before. And you can see that one is for 9 air changes per hour, the other is for 6 air changes per hour at 2 different points in time. So a benefit of CFD is it's useful for capturing thermal effects, which would otherwise be difficult to visualize within a space. So we see here the dark blue is cold air, so that's your supply air entering the space. And then over here is the general exhaust where the air is getting drawn to, and you can see the same in these images over here. These are swirl diffusers. So you can see in this image they're going across the ceiling as you would expect from manufacturer data. An important thing to recognize about manufacturer data that you get on these diffuser characteristics is that most of the values you receive are from isothermal conditions, meaning that the air leaving the diffuser is at the same temperature as the air in the room. If you take into account buoyancy, so at 6 air changes per hour, in order to meet space cooling demands, we need to supply at a colder temperature. You can see from this image that the air, due to the, buoyancy and also the less momentum that's coming off the air, is moving slower because there's less of it. You can see that the air will be instead of jetting across the ceiling and mixing before descending into the occupied space, coalescing and dropping, which could cause some comfort issues. Another benefit of CFD is you can capture other thermal effects more easily than instrumentation, such as the complex interactions of thermal plumes coming off equipment. So there's a lot of equipment located in this area of the lab, and there's solar effects coming over here. So if you wanted to physically monitor that in real time, you would need to instrument and monitor for a very long time to wait for these effects to stabilize. And with environmental conditions, such as solar or outdoor air temperature, you have very little control. Basically, you monitor what's there and then figure out conclusions. If you want to do a bunch of different tests to optimize your design based on different environmental conditions, I mean, we've experienced that where there's some tests we do where we need cold weather outside to instrument a building in order to see the effects we're looking for. But invariably, every time we go to the building, it's that one warm day and a period of very cold days, so we miss the effects. So yeah, the benefit of CFD is we have a lot of control and we can be very specific over what environment we're trying to impose. Finally, if you're trying to do tests which might be destructive, such as fire scenarios or the release of toxic substances into your space, CFD can be used to do that in a safe and controlled manner, and you're not going to destroy anything by running CFD. So to summarize the value of CFD, you can visualize every point in a space. You can perform it pre-construction. It's non-destructive. You can have very good control over your environmental conditions, and you can model thermal effects, and also you can repeat conditions in order to optimize your design. So what are we trying to accomplish? It's also important when running CFD. Well, specific ventilation requirements of labs vary widely. The overarching goals of lab design are generally the same. So you're aiming for safety and occupant comfort, and then energy efficiency is becoming also increasingly more important and relevant when looking at these studies. So many of the projects we work on are first concerned with ensuring that the ventilation scheme is maintaining the desired space conditions, so safety and comfort, and then as a secondary goal, investigating lowering the number of air changes per hour to save energy and possibly even reduce fan sizes. We also get involved in projects where clients are pursuing innovative designs and want confidence that their space will perform as it should, even if they're departing from tried and true methods of ventilation. So taking time to clearly define your project objectives helps focus the effort you put into a project and saves time and money. If you're looking at possible design options, identifying the constraints on these options also helps target the spent effort, and you spend more time exploring design options that are actually feasible. A very important part of this is to get buy-in from all your stakeholders, so your architects, your operators, owners, health and safety boards. So this may sound trivial or obvious, but it's very important for project success. Everyone has their own unique perspective, and it's frustrating for everyone if halfway through a project you figure out that you've been evaluating solutions based on the wrong metrics, or looking at design options that aren't even feasible. So even recently I was working on, it wasn't a lab, but another public space, and we've been working with the architect and mechanical engineer on a very difficult area to maintain life safety, and after back and forth we had a tentative design, which then we presented to the owner's health and safety representative, and it turns out that he preferred a different metric to evaluating life safety than we had been using, which had implications, and our design didn't meet that metric. It wasn't a complete loss because the solution we had brought us a lot of the way to meeting that metric, but at the same time we had to rerun CFD, and there was lost cost and schedule time as a result of that. So very important to get everyone's opinion before starting. So in summary, To define project objectives and constraints, you will help focus effort, so save time and save money. You'll identify constraints on the solution space and make sure you get buy-in from all your stakeholders. And now for the main question, how do I make CFD cheaper? So we discussed defining your project objectives and constraints. So making sure that CFD is indeed the tool you need. So if you determine that CFD assisted engineering design would help get the answers you need, then you may need to move to make sure that you're maximizing the value you're obtaining from the CFD work while keeping costs at a reasonable level. CFD is not a crutch or a replacement for engineering judgment and analysis. So as you move up this pyramid from design review to CFD, the level of analysis you'll be performing becomes increasingly complex, and as a result, it will also be more expensive. If you cut out the design review and engineering calculation portions of this pyramid, the gap between defining your project objectives and CFD becomes filled with more CFD simulations, which is why the CFD portion can then expand into a very expensive portion of the project. The key is to, at each level of analysis, figure out which design options are feasible and which test scenarios will drive your design. So as you move towards greater levels of complexity, you narrow down your design space by cutting out trivial cases or cases that are not feasible, and then you reduce the number of design scenarios you are considering. So when I talk about design space, that includes the various architectural and mechanical options you're considering, as well as the range of operating conditions your design is expected to perform under. So, to give an analogy, if you begin with a design review, it's like applying a chainsaw to our design space. A chainsaw is a fairly coarse tool, but you can use it to lop off large sections of your design space as either unfeasible or not conditions that will drive the design. As we move up the pyramid, this chainsaw is replaced with instruments which are much more refined. So CFD at the top of the pyramid can be compared with applying a surgical scalpel to very specific areas of the design space. And then you're also giving consideration to a high level of detail. Using a scalpel in place of a chainsaw would require an enormous amount of work. And then also if you're paying on a per cut basis, that would also be a much more expensive way to go. So to effectively perform CFD assisted engineering design, you must first use simpler analysis to narrow down the design space and then apply CFD only to a limited number of scenarios where it will yield valuable results, which will inform the design and then help drive your project forward. So as a first step, then, we can look at what constitutes a design review. The design review involves a high-level review of available mechanical and architectural information to see if we can identify likely problem areas and possibly mitigate some issues before we even get to more advanced stages of the design. So this also helps us identify scenarios of interest relating to our project objectives. So a lot of times that would be worst case operating scenarios or scenarios that would present unique challenges to the designs we are considering. So here we have an overview of two spaces to illustrate what happens at the design review phase. So two case studies. In the first, we're looking in plan view at a high density artifact storage facility. So it's not a lab, but it's similar to the type of analysis that we would do in a lab, as it's required to meet very specific temperature and relative humidity criteria in order to maintain these artifacts and make sure they don't get moldy or deteriorate. So that was the objective of the project, to maintain these uniform conditions within the space. You can see the green here represents high density shelving units. So there were a lot of them packed into this space close together, floor to ceiling, or there's a few feet between them and the ceiling, but pretty high. The blue boxes represent supply diffusers, which were angled to throw both left and right. And then there was one general exhaust, which was located high up on the wall at this end. So just from looking at this design, we can see that just from a knowledge of how air behaves, it tends to take the path of least resistance. So we want this air to go down all the way to the floor level and flush out all these aisles. In reality, it's likely going to either go across the tops of the shelves or mainly stick to these wider aisles where it can flush down easier. Just looking at this as well, we're also probably fairly likely to get short circuiting here and into the exhaust. So the design review identified that it would be very likely that we'd have to introduce some supply or a portion of the supply air at the floor, just to make sure that we're flushing down these aisles. We ran CFD to prove this case, but it turned out that we were right. And as a result of identifying this in the design review stage, the mechanical engineers and architects could get a head start on developing options as to where it would be feasible to introduce this from. We also, through this evaluation, figured out our worst case design conditions, which were likely to be extreme winter and summer. In our second case study, we had an open lab space where the goal of this was a slightly more involved project. And we are looking at a variety of ventilation schemes, as well as lowering the air change rate. So the first step was to make sure that, or find an optimal ventilation scheme for maintaining uniform mixing within the space, so ventilating out all areas, as well as maintaining occupant thermal comfort. And then the second portion would look at seeing if we could maintain those conditions while lowering the number of air changes in the lab. This one again, the blue indicates supply diffusers. So in this case, we were running swirl diffusers, and we're drawing all the supply air down to this exhaust, which is also in the ceiling. We have some equipment indicated by these red boxes. The yellowy boxes are workbenches, which are throughout the space. We have windows along one end of the lab, and then fume hoods located here and here and here, with the black indicating where the sash opening is. So as a first pass, you can see that the equipment, which is releasing a lot of heat into the space, so it was ovens, a few refrigerators and centrifuges, but mainly the ovens, when they were running, the heat from these would have to travel all the way through the lab. It would impact the occupants here and then travel to the exhaust, which is a fairly inefficient way of capturing the heat off these pieces of equipment. So we recommended that they look at the general layout before we even began CFD to see if it was possible to move some of these heat or cooling loads closer to the exhaust, so we would minimize the impact on occupants. The downside of moving it closer to the exhaust is a lot of the fume hoods are located over here. So it would be a balance between, yes, you want that local extraction of the heat, but introducing thermal plumes near these fume hoods would cause the airflows in this area to be more turbulent, and you may impact the containment of the fume hoods. So that was another thing to be considered when moving equipment around. The other thing we noted was that if they're looking at reducing air change rate, you have this fume hood with two swirl diffusers on either side. And if you remember from previously, when you reduce your air change rate, you need A, a lower temperature, and B, you'll have less momentum coming off your diffuser. So it is likely that in some scenarios, the plumes of air coming off this would drop and descend into the occupied space and would likely interfere with the containment of this fume hood. So we talked about either moving the diffusers further away from the fume hood or moving the fume hood so it wouldn't be impacted. Finally, also with moving the ventilation, the windows, we suggested that they supply some air local to the windows to help deal with solar impacts directly where they came in. So as a result of this design review, we did rework the equipment and move the fume hoods around. I believe this one was moved down to the wall over here. And some of the the equipment giving off more heat was moved down closer to the exhaust, although it had an annex down here, which I didn't show, which was helpful. With regards to supplying near the windows, it turned out it was necessary, but we didn't reach that final conclusion until after running a few rounds of CFD. So once we've completed the design review and narrowed down our cases and done some initial first pass of the design, we move on to engineering calculations. So in this phase, we start collecting more quantitative data or specific numbers to perform calculations. These calculations are one-dimensional, or they assume well-mixed space conditions. They generally include supply and exhaust rates and thermal loads, so occupants, equipment, lighting, solar, heat transfer through walls, and any relevant contaminant concentrations. So performing these calculations helps further limit the design space by providing numbers to help us identify which designs are feasible and which are not feasible. The limiter of these is often the range of feasible supply air temperatures. So sometimes in order to hit an air change rate, you need to supply at colder temperature than is physically possible from the equipment you have. Although there could also be other equipment limitations or limiting space criteria. So in this case above, we were exploring lowering the air change rate for space with very specific temperature and relative humidity criteria, and the driving case was in the winter. So just to explain that a bit more, this is the case one that we looked at before, so our high density artifact storage, and there are very few cooling loads in the room, just lighting mainly, but the outdoors, there were 2 exterior walls, and as this was quite large, the amount of heat lost through those walls was significant in the winter. So I'll look at what we do with these engineering calculations as we lower the air change rate in these, and if we want to maintain our target space conditions. For the heating case, our supply air temperature would then also have to increase. So when we hit 2 air changes per hour, you can see that the air temperature required to maintain our target space condition of 19.5 degrees is 21.8. And our maximum allowable space temperature in this facility was 21 degrees Celsius. That makes 2 air changes basically impossible to hit. 3 air changes, we're at 21 degrees, but that is a very precise number, and in the real world, conditions usually aren't quite as precise. So we went with the 4 air changes, which we could safely hit with an air temperature of 20.6 as our baseline for running CFD, or the point where we would start with investigating lower the air change rate. So this would result, if we could achieve the 4 air changes and maintain uniform space conditions, it would result in significant cost savings, as it's a fairly large space, but also it was likely that they would be able to drop a fan size. So they were very keen on running these simulations to figure that one out. Computational fluid dynamics. So once we have completed the design review and engineering calculation phases of the project, We have a specific number of CFD simulations that we run to achieve a very specific purpose. So the level of detail or complexity that we'll require in these simulations is very dependent on the application. So when we move to the CFD portion, then we start deciding on the computational domain, so the extent of the space that we'll be modeling. This can be the entire space, or like in the case of this model here, the room had 7 or 8 of these 3-bay kind of control zones for ventilation. So we ran one representative of the whole space plus an extra module on each side, so we weren't negatively affecting the results at the edge of our 3-bay module. So you don't necessarily have to model the whole space, but in some cases it's required. But if you have this repeatability, you can narrow it down. Second consideration would be the level of physics required. So if we need to model the transport of contaminants, if we need to account for the effects of thermal radiation coming off various pieces of equipment, if we need to include buoyancy, so the density or concentration of different contaminants or just heat, we should already have a good idea of the environmental conditions that we need to apply in our CFD at this point. So that's another benefit of doing the design review and engineering design phases, is you already have a lot of the numbers that you need to put into your simulation. The main consideration at this step will be how to account for the effects in your simulation. So things like solar impacts, you'll have some solar being conducted through the window, or some of the heat, and then some of the heat being radiated onto surfaces such as bench tops, the floor, in the lab. So how to account for those different means of it entering the space. An important one would be the throw characteristics of your diffusers. So when you're putting air into your space, it's not just dumping that amount of cold air. The characteristics of how it's throwing, so like swirl diffusers, getting that swirl, or if you're doing laminar diffusers, there's a certain amount of entrainment that has to occur. Getting those characteristics right is also very important when setting up a CFD simulation. So often we'll run independent tests on those diffusers to get those characteristics right before putting them into our full domain and then adding the right amount of temperature and flow rates. The final consideration is whether to run steady state conditions or transient or time accurate simulations. And then I'll touch on that one more in the case studies that we look at. So I guess for our first case study, these are some snapshots of our high density artifact storage space. So if we look at it, these are temperature results. I guess the model I was using before was a very simplified version, but this is what the actual space looked like, or a plan view. So you can see it's basically a large warehouse with lots and lots of shelves. Overhead, you can see the supply ducts with vents coming off. And then these orange lines represent the slices where we're taking results. So this one is the top, so this top image, and then this one is the bottom here. And then all these results are different environmental conditions, so summer or winter, and different air change rates that we are testing the facility at. So as a baseline, once we had a working mechanical scheme, we ran one summer case and one winter case, just as a proof of concept that yes, this mechanical scheme we had would meet the conditions required by the owner. Once we had done that, we looked at lowering the air change rate. So if you remember from the engineering analysis, we started with 4 air changes per hour. The winter condition was our worst condition, as in the summer we had buoyancy on our side. So when we were supplying air, it was cooler, which had made it more. made it more likely to drop down and penetrate in between these shelving units and reach the ground level. In the winter, since we were supplying warmer air than the space air temperature, it had a tendency to just stay on top of the shelves and not penetrate down. So the result was we would get these kind of layers of cold air near the floor that the supply air just couldn't clear out. So important point to note about these simulation results is they are steady state results. So we are taking all our environmental conditions and our operating conditions and then running the simulation until the conditions stop changing. And then we get one image of what will happen. So as this is an extreme winter design case, basically we're setting it up, we're putting it at nighttime so there's no solar benefits. We are putting it cold outdoor temperature and then basically leaving it at, you can picture for an infinite amount of time, although it's not an infinite amount of time. It's just until we're happy that we've reached one final answer. So it's a very extreme case, but it gives us an idea of where things will tend in those conditions. But yeah, so the 4 air changes was not acceptable just because we have very high level of impact here, which was unfortunate. So we tried 5 air changes per hour. We were still getting some impacts near the floor and along the wall here. We really wanted the reduction, and since this is an extreme case, we went for a second. So since we couldn't run at 4 air changes, we wouldn't be able to reduce the fan size. But for the majority of the year, conditions will not be as extreme as this. So as a proof that they could probably run at 4 air changes most of the time, we then put together a shoulder season set of environmental conditions and ran at 4 air changes. And you can see the results here are very favorable. We're getting very good and uniform conditions throughout the space. So at the end of the day, they ended up running for the majority of the year at 4 air changes. And then if the temperature and humidity readings suggested that the ventilation system might not be keeping up with the required space conditions or maintaining the required space conditions, they would switch to 6 air changes until conditions went back to an acceptable level and then ramp back down again, which still resulted in very large cost savings. The second case study I have is for the open lab, if you remember. So here's a look at what our model looked like as opposed to the simplified version that I was working with in the design review. So you can see the lab benches, there's some shelving above. The fume hoods are here in blue, the workbenches, and some equipment here in red, and then more here in green, which are the ones they moved closer down to the exhaust, which is this purple square on the ceiling. I can't see where my cursor is, but for these, we were running a time series or transient simulations. So basically, rather than in the previous ones where we get one answer, in this we could look at how the conditions evolved throughout or as time went on in the space. So this can give some valuable insights, or we won't be stuck with running extreme conditions. But at the same time, it's also more expensive. So it's a trade-off to get this extra information. For this project, we're evaluating a bunch of different mechanical schemes as well as air change rates to see which one would provide best space conditions. It was also a bit of a research project for the organization we were working on, as they have a lot of labs, and so they were looking at trying to try out some new designs or standard ways of setting up their spaces. So if we look at these images, you can see the color bar here is tracer 1 concentration, kilograms per kilogram air. So basically the way we were evaluating these spaces was filling them up with a contaminant uniformly at the beginning of the simulation, and then running the simulation to see how the contaminant would be cleared out of the room and identify if there are any dead zones where things weren't getting cleared out or if it took longer in certain areas. So yeah, you can see as you work through at the beginning of the simulation, there's quite a bit of red, which is our uniform, like our initial condition. But since this is at 0.25 air change, we can already see that at head height, which is 5 feet generally, things are already fairly clear or clearing up. So this ventilation scheme had some slot diffusers along the window to help deal with the solar effects, as well as chilled beams running down the center to help clear out. So you can see things are getting slowly drawn from the top to the bottom towards the general exhaust. And then by running these transient simulations, we could compare between the different air changes. I mean, it's a bit unfair if you're running like 8 versus 6. The 6 is going to take longer to clear because you're putting in more air, but the key is to look at the patterns and how it clears and see, or to make sure that you are indeed getting uniformity across the space. So yeah, at the end of the day, we were able to show that under the majority of operating conditions, we could run at 6 air changes per hour. And then at peak loads, they could ramp up the cooling loops within the chilled beams to help handle the thermal loads. So this is also a good story. So in conclusion, CFD is a valuable design tool, but clearly defining the project objectives and constraints will help target the effort and make the work much more efficient. And CFD is much more valuable, or most valuable, when you perform it as a component of a full engineering analysis and include a design review and supporting engineering calculations. And that is everything I had for today. Thanks for your time. Are there any questions?
Well, first, Dianthe, I just would like to say thank you very much. It's interesting to me how it's always a trade-off, I guess, to embrace some of the new technologies and you know what you get for your ROI for that. I guess it's always interesting, and clearly you showed the value of it here, so I appreciate that. Thank you. There is a question here. Let me just read it out to you here. I think this is from earlier on. Is flow considered laminar or turbulent in 6 and 9 air changes? What model have you used for the simulation?
So is it for the earlier lab questions, I guess?
Mm-hmm. I think so.
So I have to find it back. So for these ones, if that's what they're talking about, it was a turbulent flow. So we were running LES, or not LES, sorry, FDS, which is LES. So Fire Dynamics Simulator has a very good, or it's a fairly robust LES solver. So you can see in this lab, the geometry was very blocky. So everything was kind of squares, which makes it an ideal candidate to run with LES. And then you do get the benefit of the turbulent mixing, which, yeah, for a lot of things is very important. And it also provides good entrainment modeling, which is the downside of a lot of steady state simulations as well. You won't get the mixing of air on your diffuser jets. You tend to get a very smooth jet into the space as well, instead of modeling this mixing. So yeah, turbulent.
Okay, great. Not sure what this question is saying. Finally, are we convinced to use lower air changes in labs? I think it's more of a comment than a question, but I don't know if you want to make any comments about that. Should we be using lower air changes in labs?
So I think there's, based on the simulations or the projects we've done, there's a fair amount of evidence that using lower air changes does work. The flip side of that being using high air changes might not be working the way you think it is. So if we look at the our high density artifact storage, using a high air change rate, most of the calculations done are assume that the room is well mixed. And that assumption doesn't always hold true. So if you have a lot of furniture in the space, I mean, even this open lab, there were shelving units above the workbenches, which were going up to ceiling. It's very easy to get dead zones. So just counting on a high air change rate doesn't necessarily give you the performance you're looking for. And if you're going to investigate the performance, you might as well see if you can go down to a lower air change rate, because chances are if you solve your problems, it's likely that those drops will also be beneficial, and then you'll be saving not only energy but also cost on the amount of air and cooling.
Makes sense. Okay, we have another question. Does RWDI do CFD for fume hood exhaust plume study analysis to prevent re-entrainment?
CFD is a work in progress. Usually we do wind tunnel studies for that, but yes, exhaust re-entrainment is something we study.
Okay. And that is all of the questions. So unless anyone has any last minute questions, we'll sign off. And again, thank you very much. It was quite informative.
All right, thank you.
Okay. Everyone have a great afternoon, and thanks for participating today. Thanks very much, everyone. Thanks, Dianthe.
Thanks.